All right, welcome everyone. So a couple of announcements. Based on what we're talking about in class today, I recommend trying part A of the out of the book problem that's on homework 1, that's due on Friday. And on Thursday, we'll be working on how to use R, which is a statistical software package, statistical programming language, to solve problems in probability. So you can help out with this by following the instructions in the Installing R and RStudio document that's here on Canvas. R is free, it's open source, so you can install it on your laptop. You can also get to it through the virtual lab, but personally, I think it's easier to just have it directly on your laptop. So if you would, please install R and RStudio on your laptop if you don't have it already, and then bring your laptop to class on Thursday so that we can go through some examples of how to write code in R to help us verify or generate hypotheses about our solutions to some problems in probability. Sounds good? All right. So let's start with a problem. If you put the letters M, A, T, and H into a hat and then take them out in a random order, what's the probability that they happen to come out in the order that spells the word math? Take a minute to make a guess about how big that probability is. All right, so let's figure this out. Let's go ahead and assume that we're choosing letters uniformly at random. So this means that we're equally likely to choose any of the letters that is currently in the hat. All right, so how can we compute this probability? Well, if we're choosing letters uniformly at random, we're equally likely to pull out any of the letters that's in the hat. Then all of the possible orders of letters are equally likely. So M-A-T-H is just as likely as H-T-A-M. So in that case, the probability is just going to be the number of orders that satisfy our goal divided by the total number of orders. Well, in this case, our goal is to spell the word math exactly. So there's only one order that's going to do that. So let's focus on this denominator. So the total number of orders we can think about as being the number of choices that we have for the first letter. We have 4 choices, times the number of choices for the second letter. Well, once we've taken one letter out of the hat, there are only 3 letters left. So there are 3 choices. Times the number of choices for the third letter. Well, we've taken 2 letters out, so there are 2 letters left. Times the number of choices for the last letter. And at that point, there's only 1 letter left, so there's 1 choice. So we have 4 times 3 times 2 times 1, or 24 for our denominator. So overall, our probability of getting back the word math is 1 over 24. So this is an example of a permutation where if you have n distinct objects, so all the letters in this case were different, then the number of ways to take an ordered set of R of them is given by this formula. So in the example we just did, n was 4. We had 4 letters total. We wanted to take 4 of them out of the hat. We wanted to take them all out of the hat, so R was 4. And we were interested in the order. The order mattered, so it was an ordered set. And what we did is exactly this. So 4 times 3 times 2 times 1. So 4 times 4 minus 1, so times 3, dot, 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 multiplying all the way down to n minus r plus 1. So in this case, that would have been 4 total letters minus the 4 that we were taking out of the hat. So 4 minus 4 plus 1. So multiplying all the numbers from 4 down to 1. A shorthand way of writing this is as n factorial is going to be the product of all the integers from n to 1. And then we would just divide by n minus r factorial. So just get rid of all of the factors that we don't want to multiply. So n minus r minus 1, all the way down to 1. Questions about this formula? As a note, if you have a TI-83 or TI-84 calculator, the way to get this is with the math button, and then choosing PRB for probability, and then NPR for NPIC R or NPermute R. All right, let's try another problem. Math class has 30 students. What's the probability that at least 2 people share a birthday? And as we do this, we'll assume that all birthdays are equally likely and there are no leap years. So take a moment to think about how big you expect this probability to be. All right. Someone who hasn't seen this problem before, can you give us what your guess is about how big this is going to be? How about a range of possibilities? Let's say raise your hand if you think it's going to be closest to 0.001. Raise your hand for 0.01. 0.1? 0.5? All right, let's try it. All right, so first of all, the probability that at least 2 people share the same birthday, using the complement rule, is going to be 1 minus the probability that all birthdays are different. So the complement of at least 2 people have the same birthday. If that's not the case, then it must be that all the birthdays are different. Agreed? All right, so let's focus on finding the probability that all birthdays are different. That's going to be easier here. Start by thinking about, what does a sample point look like? So remember that a sample point is a simple event. So it's a value in our sample space that can't be decomposed. Well, the experiment in this case is asking 30 people what their birthdays are. So the sample point must be a list of 30 days that we found out from each of those people. And let's go ahead and put them in order alphabetically by people's names. So we have a fixed order in which we're writing these dates. So for example, first person says March 5th, and then the second person says December 30th, and then the third person says June 17th. We get 30 of those in one ordered list. That'll be one sample point. All right. So if we're finding the probability of all the people having different birthdays, our denominator should be the total number of sample points. It should be the total number of possible choices of 30 days in our list. And this includes, there could be repeats, there could be no repeats, either way. So the denominator is going to be 365 raised to the 30th. We have 365 choices for the first person's birthday. We have 365 choices for the second person's birthday, ... down to the 30th person. The numerator is going to be the number of combinations that fit our goal of having all birthdays be different. Once we find that, then we'll take 1 minus that to get the probability of at least 2 people having the same birthday. Well, if that's going to be the case, we have 365 choices for the first person's birthday. Then for the second person, we have 364 choices because we're trying to have this person's birthday be different from the first person. Then 363 choices for the third person because we don't want them to match either of the first 2 people. And so on, down to 365 minus 29. To get all the 30 people's birthdays to be different. So that turns out to be 365 times 364 times ... down to 336. Or thinking about this in terms of the permutation formula that we saw in the previous slide, this is 365 factorial divided by 335 factorial. So we're taking all of the possible values, 365 times 364 times ... times 336 times 335 ... down to 1. So 365 factorial is our numerator, and our denominator is 335 times 334 times ... down to 1. So when we do that, the 335s cancel, the 334s cancel, ... down to the 1s cancel. So all that gives us our numerator for the probability of everybody's birthday being different. All right, so I did this in R because these numbers end up being pretty big for the numerator and the denominator. So here's what I did. Started with prob equal to 1. And then for each number from 365 down to 336, multiply the probability by that number, so 365 over 365 times 364 divided by 365, and so on. We end up with 0.29. So that's the probability that all 30 birthdays are different. So the probability that at least 2 people have the same birthday is 1 minus that. So it ends up being 0.7. So it's actually bigger than the 0.5. It was our biggest option on our list. Questions about this? This is assuming that all birthdays are equally likely, which isn't quite true. If you do account for different days being more and less likely for people's birthdays, the probability actually increases slightly from 0.7. All right. So let's think about this problem. How many ways are there to assign 20 people to 4 jobs if job A takes 6 people, job B takes 4, and jobs C and D each take 5? So here we have n distinct objects, so n is 20 in this case, and we're trying to partition them, so divide them up so that everybody gets assigned to exactly 1 job, into k groups. So in this case, we have k is 4. And we care about the order of the groups. So job A is different from job B, but we don't care about the order of people within groups. So if Alex and Betty both get assigned to job A, that's the same as Betty and Alex both getting assigned to job A. And then we have the number of people assigned to each of the k groups should add up to the total number of people. So this is sort of related to our permutation problem that we saw earlier, right? Because we've still got distinct objects and we want to pick subsets of them. But this should be sort of less than the total number of orders of 20 people, because we don't care about the order within groups. We don't care about the order in which people get assigned to job A. We just care about which people got assigned to job A. The number of ways to do this is n factorial divided by the factorials of the numbers of people in each of the groups, or numbers of elements in each of the groups. The reasoning here is, if you think about covering up the denominator here, if we just had n factorial, that would be the total number of orders for n objects. But we don't care about the order within groups. So we have, say, n sub 1 is 4, so there are 4 people assigned to job A. We only want to count each combination once. We don't care about the 4 factorial different orders in which people can get assigned to job A. We only care about the combination where people 1 through 4 got assigned to job A, and a different combination where people 2 through 5 got assigned to job A, and so on. So we need to divide out the possible orders of people assigned within each group, because we don't want to count those. Questions about this? Said that. So in the case of our job example, we have 20 factorial divided by 6 factorial, 4 factorial, 5 factorial, 5 factorial. So 9.77 billion. All right. So in addition to permutations, so n pick r, maybe in a previous math class you've seen combinations, n choose r. So these have the symbols n over r in parentheses with no line between them. It's not a fraction. NCR written sort of vertically or NCR written horizontally. This is the number of ways to choose R objects out of n distinct objects where order does not matter. So n choose R turns out to be equal to n factorial over r factorial times n minus r factorial. Think about why this is true. Any ideas? Niall?
Is it maybe because order doesn't matter? So when we were doing permutations, every time you go to the next step, you are accounting for the fact that there was already something in the previous spot. So we went from 2019 to 1817. But in this case, the order doesn't matter. So we can just, I guess, we could call it replacement.
Yeah, so we could think about this as being n factorial over n minus r factorial. So that's the number of ways to pick R objects where order does matter. And then divide that by r factorial. So this would be the number of orders of the R objects that we chose. Go ahead and share this with. Anybody have a different possible explanation? Maybe relating this to the formula we saw on the previous slide? Share the screen again. We can think about this as taking n objects and dividing them into two groups. There's the group that we chose and the group that we didn't choose. And we don't care about the order of either one of those. So we can think of our n choose r formula as being a special case of the formula we saw here. We have n factorial divided by the number of individuals in one group. So r factorial is the number of orders for the group that we chose, times n minus r factorial is the number of orders for the group that we didn't choose. So either of these explanations works for why the formula for n choose r is what it is. Questions about this? All right. So try using this formula to solve this problem. A company has 20 new employees. 6 of them will be chosen for a new computer-based training. How many ways are there to choose who gets the new training? All right. So this is going to be 20 choose 6. So 20 factorial divided by 6 factorial times 14 factorial. Someone want to tell us what that gives on your calculator? 760?
38760.
38760? Does that agree with what other people got? Cool. All right. In poker, a flush is 5 cards of the same suit. How many ways are there to get a flush in a 5-card hand? And as a note, this is a standard deck of playing cards, which has 52 cards, and there are 4 suits of 13 cards each. Try using the methods of counting that we've talked about so far to compute this. There are a couple of different ways that we can do it. So one way that we could do this would be to say, first, we want to choose the suit. So we have 4 choices for that. So 4 choose 1. And then there are 13 cards in that suit. We want to choose 5 of them, and we don't care about order. So we first choose the suit, then 5 out of the 13 cards in that suit. So 4 choose 1 times 13 choose 5. That gets us 5,148. The other way we could do this problem would be to say, first we choose 1 card, and there we have 52 choices. And then for our second card, we want to choose a card from the same suit as whatever the first card was that we picked. So there are 12 choices from that suit that are left. Then 11 choices for the third card from that same suit, then 10, and then 9. But when we do this computation, we've treated it as order mattering. And in poker, it doesn't really matter which card you get first. You just care about, at the end, what 5 cards are in your hand. So then we need to divide by the possible numbers of orders, the possible orders for these 5 cards. So we divide by 5 factorial. And that gets us the same answer, 5,148. Questions about this? So now if we wanted to know the probability of getting a flush in 5-card poker, this number of ways of getting a flush is going to be our numerator. 5148. What should our denominator be? Okay.
Would be 52 factorial.
That would be the number of possible orders of all 52 cards in the deck, which isn't quite what we want. What we want is to know how many possible 5-card hands we could end up with. Other ideas? There are 52 cards in the deck. 9.
Would it be 52 factorial divided by 47 factorial?
Divided by what? Sorry?
47 factorial?
47 factorial? Yeah, we're getting closer. If we do that, so this would be the number of ways to pick 5 cards so that order mattered. But because we computed the numerator, saying that order didn't matter, we want to do the same thing in the denominator. So our denominator is going to be 52 factorial divided by 47 factorial times 5 factorial, or in other words, 52 choose 5. The total number of ways to choose 5 cards from a set of 52 where we don't care about order. Questions about this? Sam, question? Okay. Share the screen again. All right. So now that we have some extra tools in our tool chest, let's come back to the same idea from the beginning of class. Let's say we put the letters B-A-N-A-N-A in a hat and take them out in a random order. And we want to know the probability that they spell banana. So this is similar to our problem about the word math, But it's a little more complicated because now we have some letters that are duplicated, where we don't care about whether the second letter is the first A or the second A or the third A. We just care that it's some A. But we can use the tools that we talked about here to solve this. It's sometimes helpful to start by thinking about labels on the letters. So say it's B, A sub 1, N sub 1, A sub 2, N sub 2, A sub 3. And come back to our basic idea, is that if all the orders are equally likely, then the probability we're interested in is the number of orders that spell banana divided by the total number of orders. And the total number of orders is just the number of possible orders on 6 letters. So 6 factorial. So we've got the denominator. The numerator is going to be the number of orders that spell banana. And here, we can come back to our principle from the very start of class of just thinking about how many choices there are at each step of the way and multiplying the number of choices. So for the first letter, we need that to be a B, so there's only one choice. For the second letter, we need that to be an A, but there are 3 A's. It could be A sub 1, it could be A sub 2, or it could be A sub 3. For the third letter, that needs to be an N, and there are 2 possible N's, N sub 1 and N sub 2. For the third letter, that needs to be an A again, and there were 3 A's, but now there are 2 A's left because we already used up 1. And then for the fifth letter, that needs to be an N. There's only 1 N left in our bag. And for the last letter, that needs to be an A. There's only 1 A left in the bag. So the number of orders that spell banana is 3 times 2 times 2 times 1 times 1 times 1. So that's 12. So the probability then is 12 divided by 6 factorial. And that turns out to be 1/60th. Questions about this? Let's do, hang on. Let's come back to our example assigning 20 workers to 4 jobs. Let's suppose that job A is everyone's least favorite. And all the workers who are African American, all 4 of the African American workers who work at this one small company, happen to get assigned to that job. Is that evidence of discrimination? In other words, what's the probability of this happening if the workers were assigned randomly? So if this could happen pretty easily by chance, if it has a pretty high probability, then we can go ahead and give the company the benefit of the doubt. But if this is really unlikely to happen by chance, then we want to be more suspicious. Then we want to maybe take that company to court for discriminating against its African American workers. So remember that this was how we set up the problem before. We had the total number of ways to assign jobs was 20 factorial divided by 6 factorial times 4 factorial times 5 factorial times 5 factorial. So that's going to be our denominator. That's the total number of ways to assign 20 people to these 4 jobs that require 6, 4, 5, and 5. the number of ways to assign the jobs so that all 4 of the African American workers get assigned to job A looks like this. So we start out by saying, we're just going to go ahead and achieve the goal that we want to find the probability of. Go ahead and assign all 4 of these people to job A. There are 16 people left to assign among 4 jobs still. We have 2 spots left in job A, and then 4 spots in job B, 5 spots in job C, and 5 spots in job D. So this is going to be our numerator. So our probability is this 16 factorial over 2 factorial, 4 factorial, 5 factorial, 5 factorial, divided by the number of total ways to assign 20 people to the jobs that we saw earlier. We can simplify this sum by canceling like terms. So we can cancel the 4 factorial, 5 factorial, 5 factorial from the numerator and the denominator. And this ends up being 16 factorial over 2 factorial, so I've written that here, divided by 20 factorial over 6 factorial. So I've inverted that denominator to simplify it. So we can simplify this more to help reduce the size of the numbers so that your calculator needs to work with. The 20 factorial contains 20 times 19 times ... down to times 16 times 15 times 14. We can cancel those with the 16 factorial. So from the 20 factorial, we're left with just this first part, 20 times 19 times 18 times 17. And then we have times 2 factorial in the denominator, 2 times 1, so we get a 2. And then times the 6 factorial in the numerator. And that simplifies down to 1 over 19 times 17. So that works out to be 0.0031. That's a pretty small probability. Commonly, we use a threshold of either 0.05 or 0.01 as a threshold for what we think is too small to occur just by chance. So if this is the first time these workers have been assigned to these jobs, and the first time it happened so that all of the African American workers got assigned to the least favorite job, this is unlikely enough that we should consider bringing a suit against this company. Questions about this? One more problem, sort of relating probability to algebra. In the expansion of x plus y to the 8th, so we're going to multiply out x plus y times x plus y 8 times. What's the coefficient of x to the 5th times y to the 3rd? So let's think about how this is going to happen. We have x plus y times itself 8 times. And each time we multiply to get a term of the result, we're taking one term from each of these factors. So maybe the first time we go through, we pick all of the x's. That's going to give us an x to the 8th term. And maybe the next time we go through, we pick the x's in each of the first 7 terms, but then we pick the y. That'll get us an x to the 7th times y. But we could do that a total of 8 times, picking 7 x's and 1 y from a different factor. So when we add these together, we'll end up with a total of a coefficient of 8 copies of x to the 7th times y. So the idea is, when we do this out, how many copies of x to the 5th times y to the 3rd do we end up with? Well, we have a total of 8 factors. And we need to choose 5 of them to contribute an x, and 3 of them to contribute a y. And we don't care about the order. Using that information, try to solve this problem. All right. So we have a total of 8 things, and we want to choose 5 of them to belong to one group, and 3 of them to belong to a different group. So we're choosing from among the factors. So like where x plus y would be one factor, and we want to choose 5 of them to belong to the group that's contributing an x, and 3 to belong to the group that's contributing a y. So that's going to be our same formula that we used to assign people to jobs. 8 factorial, so n factorial, total number of objects we want to arrange, divided by the number of orders for group 1 and the number of orders for group 2. And that works out to 8 times 7, or 56. Questions about this? Time.
So we have 8 factors, but we have 8 x's to choose from and 8 y's to choose from. So does that complicate the problem at all, or why does that still kind of stay the same as our previous problem?
Good question. From each factor, we only choose one of either the x or the y. So we can think of it as choosing a factor to give us an x or to give us a y. So because the x's and the y's are linked, it stays the same as in the previous problem. Pooja?
So I just did like 8 choose 5, or like do 8 choose 3, because then automatically the other ones would have to be the other group.
Yep.
That's just, yeah.
Yeah, exactly. It's the same thing. It's the same formula. Because you can think about choosing which of the factors are going to give you an x, And then automatically, anything that you didn't choose to give you an X will give you a Y. If this were a problem about like X plus Y plus Z to the 8th, then you would want to think of it in terms of the jobs problem, not in terms of 8 choose 5. But if it's only 2 options, then yeah, it's the same either way. All right, thank you all for your attention. I will see you on Thursday. Please bring your laptop so we can do stuff in R.